Ben rahatım.
Başladı mı? We started talking about paging has addressed a number of problems, and we started talking about the problems with the paging. The most important problem with the paging is that the translation from the mapping from the virtual address to the physical address must be very quick, very fast. And the second one is the virtual address space is large, so the page table will be very large. I mean, in the early days, maybe the virtual address space was maybe 2 times the real memory, the physical memory. Nowadays, the virtual address space for some systems, and we will see for some systems, I can do this kind of stuff. Okay, show to the power. If I have 64-bit address spaces, then I have this many addresses in my virtual space, but I have only a few gigabytes of physical address space. So this page table would be very large. How do we solve these problems? We are going to look at these. We said that the first solution would be the large table sizes. We would say that we would use something like a cache between the page table and the main memory and the MMU. Okay, MMU keeps only a few page table entries, maybe 8 or 16, like the example that I showed you last time. So it would be very fast for those 16 pages. So when you make a memory reference, and if the page that you are referring to is in the MMU, in this TLB, the translation local site buffer, then everything will be very, very fast because it is like using a cache, and you would reference your memory. If it is not inside that TLB, then it's a miss. It will be the same thing as the getting a miss from a cache memory. So we talked about these, and this was some examples. So my TLB in this case has only 8 entries. But my page table could be very, very large, maybe megabytes of data in it, but I don't care because I use these. Okay, and then we said that many TLBs are implemented with the management of the TLBs are implemented with the operating systems instead of implementing them on the MMU, because on the MMU we need more space, more registers. Instead of embedding this code on the MMU, we would handle them with the software on the OS. That's why we are looking at this memory management stuff with the TLBs, and we talked about soft misses, hard misses, etc. So this is the last time where we left. Okay, then we will pick it up from here and continue. Okay, the problem with
major page fault and minor page fault
what? Major page fault and minor page fault? I mean, when you get a page fault, okay, each process has its own page table, right? So remember, the page tables are like like these. So I have only 16 entries in my page table, and my process has these. Another process has its own page table. Okay. So if for this is for process number 1. For process number 2, it has its own page table. Let's say it has the same for the let's say for the 10th page location, it has this number 111. Okay. So for this one, for the 10th location, it doesn't have anything, so it is not loaded, it is invalid, right? So when I refer to this page table, I would say that I don't have this page in the memory, but some other process has it in the memory. Okay, some other process has it in the memory. So it's a page fault for this page table, but the page I am looking at actually are in the memory. So all I need to do is get this number from here and write it here and mark this as 1. Okay. So two processes are sharing the same page.
Page fault first level cache'te bulunamadığı zaman yoksa main memory'de bulunamadığı zaman.
Page fault is Here. If you don't find it in the page table, it's a page fault. But there are two types of page faults. One is the minor page fault, which is this one. The second one is the major page fault, which is the page you are looking for is not in the main memory. It needs to be brought from the list. So both of them are called page faults. So if it is not in the page table, then it's a page fault. If it's a minor or not minor, major, it depends on if the page is available in the memory or not. Okay, another questions? So these are the things that we looked at last time. So using TLB's translation local site buffers is good for making this mapping from the virtual address space to the physical address space fast. Okay, that was for the fast. Remember, there was another problem. The second problem was the page tables were growing very, very large. Where do we keep them? If you keep them all in the memory, sometimes they would get very, very large. They would take lots of memory space. Most of the time, maybe some of them will not be used at all. So what we do is we have this multi-level page tables. Let me show it to you with using some kind of a figure. Okay. So at the top level, in this case, I have 1K of page table entries. Okay, this is the top level. So my virtual address is like this. Okay, this is the offset into the page table. Okay, and this is the offset for the top level page table. Okay, get this 10 bits, address it in this page table, get a number from here, and following this number, go to one of the second level page tables and get the page address for the physical memory. So I need to make two lookups, one from the top level page table, one for the second level page table, two of them. So the nice thing about this thing is that I can keep only this top level in the memory and some of these second levels. Not all of them have to be loaded into the memory. So how many of them are there? This is just one. There are total of more than there are more than 1,000 pages like these, and I don't have to keep all of them in the memory. Only a few of them. Only a few most frequently used tables of the used tables needs to be loaded on the memory. Because otherwise the numbers is very, very high. I don't want to keep them all in the memory. This is called multi-level page tables. So the nice thing about them is that they don't say space. Okay, they use more memory because I need to keep this memory too. They don't say space, but they save space on the memory, on the main memory, because I don't need to keep all of them in the memory. Some of them could stay on the disk. Wherever I need them, I will get them from the disk, and maybe some of them will be written to the disk. So only a small number of them will be used at the same time. So the problem we are solving here is that we are solving the problem with the large requirement on the main memory. So the number of page entries are not small. It is the same, maybe a little bit more. But the number of the entries that you are keeping in the memory is small enough. Okay, any questions? So this is called multi-level page table, and it addresses the problem of needing larger runs of main memory. Okay, so this is a very popular technique actually. It has been used for the last 30 years maybe. 1985 Intel 8368 processor. It had two levels of page table. Okay, so the first page table is this one. It has 2 to the power. Okay, 2 to the 10 entries. That is 1024. Okay, this is the size, and then I have this many these pages. Okay, I have 124 pages, and I have these pages, this many pages, and this is the size of the page frames. So if you multiply them, this would be the address space. So I can address 2 to the power 32 bytes using this kind of a page table structure, 2-level page table structure. Okay. So this is like 4 gigabytes of memory, 4 gigabytes of main, 4 gigabytes of what? Physical or virtual? Physical or virtual? Virtual, it's not physical. Because in 1985, we are not talking about 4 gigabytes of memory. There was no such thing. Okay, so 4 gigabytes of virtual memory, because remember, this is my top level page table, second level page table. Okay, if I combine them, okay, this is my virtual address. Virtual address is how many bits? 20 plus 12, okay, 32 bits. I can address 2 to the power 32 addresses using this virtual table, virtual address. But this address needs to be mapped. So using the first 10 bits, I make a lookup. Using this lookup, I make another lookup from one of these tables. And from that table, I get the physical page frame address and attach offset to it and get the real physical address. So this is 4 gigabytes of virtual address space. It was very, very big in those days. But 10 years later, when the Pentium Pro came to the picture, this kind of structure was not enough. So instead of using 2-level page tables, now they have 4 levels. Okay. So at the top, I have this many elements, 512 entries at the top level page entry, and this is the second layer, third layer, fourth layer, and this is our virtual pages. And if I multiply them, this is the address space that I can address in my virtual address space, and that's a very large number actually. So it's this is 2 to the 10 is kilobyte, then megabyte, gigabyte, terabyte, and this is the petabyte, I don't know. So it is very close. So 1/4 of this one, okay? So it is 256 gigabytes, right? Is it correct? 256. What was this one? This is kilobytes, megabytes, gigabytes, and terabytes. I get 256 terabytes of virtual address space. That's a very, very large memory space. That's a very, very large memory space. So in 1995, close to 2000, we could have these kind of memories, virtual memories available. But now we know that most of the computers we are using, they don't have these kind of memories. They have maybe on the average 8 gigabytes of memory or 16 gigabytes of memory. So the available physical memory is much smaller than the virtual memory. And using this 4-level page table lookup, I can handle these kind of address spaces. So the downside is I need to make one lookup, second lookup, third lookup, and fourth lookup. After the fourth lookup, I get the physical address. So my hardware needs to be very, very fast. My hardware needs to be very, very fast. If everything is inside the translation look-aside buffers, then I should be fine because it's a very fast hardware. Okay? Any questions? So these were the methods that kept the, okay, this was the technique. Okay? Get 10 bits from here and look it up from a page table and use that address as a physical address. That was the idea with the page tables. Then there was another invention. It's called inverted page tables. It just worked just the opposite way. In this design, there is one entry per page frame in real memory. So there is one entry per page frame. Remember the number of pages and number of page frames. Which one is larger? Number of pages or number of page frames?
Pages.
Number of pages is much larger, right? And we look at the numbers, it is much larger. So instead of keeping one entry per page, we keep one entry per page frame. Okay? Instead of one entry per page, we keep one entry per page frame. So just the opposite, inverted page tables, that's called. Okay. So we do this rather than one entry per page of virtual address space. So we invert the structure. Inverted page tables save lots of space because I don't need to keep that kind of large numbers. I mean, this is a very large number. This is a very large number. Okay, but this is not a very large number, 4 gigabytes. So it is 2 to the power 32 compared to this one. So this is not a very large number, but this is a very large number. If I have a page frame table of this size, it is much better than this. It is much better than that. That's what inverted page tables are doing. Inverted page tables saving a lot of space, but the problem is when you get a virtual address, converting that virtual address to the physical address becomes a problem. Previously, we just take the first 10 bits and use that 10 bits as an array index, right? And array indexing is very, very fast. We know that from our C classes, okay? It is very, very fast. In this case, I get the index. There is no place. I mean, my structure is like, okay? My structure is like, this is my page frame table, okay? Page frame table. And these are the physical frame addresses, okay? 0, 0, 1, 0, 0. So the problem here is that the address that I am looking for is inside this array, not the index part of it, but the inside the array. When process and references virtual page P, the hardware can no longer find the physical page by using P as an index. Okay, I don't have it anymore because I don't have a page table anymore. Instead, it must be searched. It must search the entire inverted page table for an entry. I must make a search inside this table. Okay, when I find the virtual offset, I would say that okay, this is my physical page address. Okay, so I need to make a search inside this table. And searching is very, very slow. Okay, searching is very, very slow. I need to make a linear time search. I mean, remember, this is a lookup, and we didn't keep our page tables in the main memory because main memory was very slow. Instead of, I mean, this is much worse than that. It is much worse than that. Instead of using an O1 slow algorithm, we are trying to use an ON, much slower algorithm. This is bad. So instead, we have to search this table. The solution is maybe we can use an associative memory, like the cache, TLB, and hash tables. So for the hash tables, remember the hash tables maps, Java maps. Okay. If I use a map, okay, inside the map, this would be my virtual offset, and this would be my P, the physical page frame address. Okay, that would be a map. And maps can be implemented using hashing techniques, actually using hash tables. So on the average, what would be lookup cost from the hash table? O1, right? We can do it with O1 complexity. Hash tables are, if they are not, dot, fill in the blank, okay? If they are not, dot, hash tables are very, very fast. If they are not, question, if they are not, fill in the blank, hash tables are very fast. If they are not loaded, yes. If they are not loaded, then hash tables are very, very fast, right? If the loading factor is 1, that means that I will have 1 item per hash key. That would be, I wouldn't need any, I wouldn't expect any collisions. I wouldn't expect any very long linked lists. So hash tables would be very large. So instead of making a search, I would make a lookup table, okay, map, hash table, using the key as the virtual address offset, okay. And when I get the hit, I would get this physical page frame address from the hash table. But before that, I would use a TLB, okay. Use a TLB first, okay, because in the associative memories, making this reverse lookup is easy, okay. get the virtual address, okay, get the virtual address. Using the TLB, get the page frame number. If there is a miss, then use this hash table. Use this hash table to get the physical addresses like that, okay? So if I have a 64-bit addresses, then I can address this kind of space, 2 to the power 64. And it is possible with today's computers because we have 64-bit CPUs, right? So address space is very, very large. So if I use a traditional page lookup table, this would be the size of the page lookup table. Why? Because in this 64-bit, okay, 12 bits are for the page offset. The rest of it, that is the 52 bits, would be the offset, would be my virtual address V. V part would be 52 bits, and the offset part would be the 12 bits. That's why my page table would be this large, 2 to the power 52. Okay, very, 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 very large, very, very big. If I have this kind of a, memory space, using multi-level page tables doesn't solve this problem because multi-level page tables doesn't lower your memory need. All they do is they keep most of your page tables on the desk. Okay, so it doesn't solve this problem. But if I use this inverted page tables, all I need to do is, let's say I have 1 gigabyte of physical memory, okay, with 4 kilobyte page frames. That means that 1 gigabyte is 2 to the power 30, right? So I have 30 bits. This 12 bits is for the offset, and 18, yeah, and this 18 bits are for the virtual part, okay? So the lookup part. So 2 to the power 18